Today we're going to analyze a Linux ransomware. Usually, most ransomwares are designed and coded to run on Windows operating systems or to infect Windows operating systems. And we've analyzed plenty of ransomware samples before, but today we're going to analyze a sample that's designed to run on a Linux operating system or in a Linux environment. Okay, so you are in the shoes of a malware analyst or a defender, and you want to start your analysis. The first thing you want to do is to take a look at the file. To understand the nature of the file, we use the command file. And as you can see, the file is designed to run on Linux operating system 64-bit. And here is information about the shared libraries. And the name of the file is base encrypt or bescrypt 3.2. So that is the file. So how do we start the analysis? So we can use multiple tools. For example, Ghidra can be used to take a look at the source code of the file. If we use Ghidra for this scenario here, let's close this one. Okay, so once we open the file with Ghidra, we have a list of the imports, exports, functions, and other information. What we are interested in is analyzing the main functions. Under the main function, there is this line. Line 5, there is a call to function named process directory. The process directory function takes two arguments. The first argument appears to be a directory, and the other argument appears to be a string. So this is a directory, and given that we know this is a ransomware, we can suppose or assume that the files that will be encrypted will be found under this directory. So this is the subject of the encryption process. It is the directory specified here. Now, if the ransomware was supposed to encrypt the entire Linux file system, then this would be only the /. The argument will be only /, indicating that the ransomware will encrypt the whole file system. But here the directory which will be encrypted is explicitly specified. Okay, and this is the string. We're going to assume that this string is the encryption key. These are only assumptions. We're going to have to follow through to the process directory function to take a look at more details. So under the list of functions, we can see the process directory. And indeed, the process directory takes two arguments. As you can see, parameter 2 and parameter 1 taken from the main function. So the directory, which will be encrypted, and what appears to be as the encryption key are passed along the parameters here, right? And then we can see a couple variable declarations, and here we can see a while loop, a while with combinations of if and else that loops through every single file found under critical data, right? It takes into account all file extensions, text, SQL, PDF. It encrypts all of these extensions, and then upon successful identification of these files, it prints encrypting, indicating that it is now encrypting all the files. After printing the statement, we can see a call to a function named encrypt_file. This function takes two arguments. As you can see, there is a common argument between encrypt file and process directory. It is parameter 2. It is mentioned, or it is taken as an argument in both of these functions. Now, if you go back to the main function, you can see that parameter 2 equals to this string. So our assumption that this string is the encryption key looks to be true. Let's go back. Now we're going to have to follow through to encrypt file function. Let's see where is the encrypt file function. You can see it's here. Now we take a look at the encrypt file function. We can see it takes two arguments. As you can see, the first argument or the other argument is the encryption key, and parameter 1, if you go back to the first call, it is the variable named local 418, which is defined here. Now local 418, let's follow through this variable to see what it does. So local 418, it is the variable that controls the file being encrypted. So if you go to the encrypt file here, the main two arguments taken into account are the encryption key and the file being encrypted. Here we can see a couple if and else statements to control to verify the existence of the file. So if the file doesn't exist or there's a problem opening the file, we can see error opening the file. And upon successful encryption, we can see we have the fwrite. The fwrite function writes this statement to the user, or creates a file and writes this statement inside this file. The file name is local_40. And look at this. Line 17, we have a variable declaration, local28. The local28 stores the value or the contents of the file being encrypted. As you can see, fopen is used to open the file in a read binary mode. So here we are actually reading the original contents of the file. And then we can see here a couple declarations of malloc to allocate the appropriate size for the file, or for the output file, the encrypted file. And scrolling down, we can see that line 34, the local28 variable that was defined earlier opens another file with with the write binary. Now, this is what happens here. At line 34, the encryption process starts, where the file or the original content of the file is being encrypted after the file is opened in write binary mode. And then the file closes, and the original file, look at this one. Line 48, or line 49, there is an if statement on the original file. Now, what happens here is that the encryption function here, after encrypting the original files, it deletes the original files after encrypting them. So we have this if statement that if the program encounters an error deleting the original file, we see this error statement printed out. So that is the dissection of the source code. Now, again, the key takeaway here is, or the main key takeaway here is that this is the encryption key. Now, usually when you analyze a ransomware, it's very recommended to open first the ransomware using a binary analysis tool such as Ghidra. You want to find any hints of these critical information, such as encryption keys, directories being encrypted, what is the mechanism that the program follows in order to encrypt the files. And this is very important if you want to start the decryption process. So once you get once you get the decryption key here, you will be able to create maybe a Python script where you feed the Python script the encryption key and perform a simple XOR operation on the encrypted files. So knowing the mechanism found here, we can create a similar while loop found under the process directory. A similar while loop can be created where the program follows or loops through every single file found under the Forella critical data. Now, after the encryption process, these files are supposed to be encrypted. Now, looping through these files with the encryption key and with a simple XOR, you will be able to decrypt these files. Okay, now you want to analyze the file with radar. You can just use radar2 and then analyze with AA, and then you can print the main function or use AFL. Here you can see the list of the functions. AFL is equivalent to examining the functions using Ghidra. Going back to radar2, we can see the encrypt file function. We can see the process directory function. We can see the main function. We can start with the main function by printing the contents. So BDF at main will print out the contents of the main function. Here we can see the declarations or the prologue, and we can see the string, or what was known as the encryption key, being defined here, and it's loaded. The effective address of this was loaded via Lee and stored under the RAX register. And then the contents of the RAX register was supposed to hold the encryption key are stored under this variable var br8h. br8h happens to be the register base pointer. And then we have the directory, which will be the subject of the encryption process. Its effective address was loaded using Lee and stored under a RAX. In turn, the value of this was, or value of which was moved to this variable here. And then we can see the call to the process directory function. Then you can jump to process directory function by using pdf at, and you can use the name of the function, and we can see, we can examine the assembly code of this function. Starting from this line. Okay, now after analyzing the source code of the ransomware, after finding out the encryption mechanism, you are ready to start the decryption process. Now let's dynamically analyze this malware. We can use AnyRun to accomplish this. So I'm going to use AnyRun. I'm gonna restart, click on restart here, this task. Here I uploaded the file. Okay, I chose Ubuntu as the target OS, and here start object from, I chose desktop because I want the files to appear in the desktop. Run public analysis. Okay, so if we start here, let's open the terminal. Okay, now cd to desktop. This is the ransomware, right? Now, if you attempt to execute this ransomware, we can type, or we can first grant the ransomware the execution permissions, sudo +x. We forgot the main command. Okay, if we attempt to execute, we get this error opening directory for critical data. So why this is happening? Because if you remember, guys, I told you at the beginning of this analysis that the subject of the encryption process is a directory specified here. It is clearly specified that the encryption process will encompass the files stored under critical data. The directory is explicitly specified. While in other circumstances or in other scenarios, this might be only indicated by a /, right? To indicate that the ransomware will encrypt the whole file system. Let's go back. So in order to solve this problem, we're gonna have to create a directory named, so maybe sudo make directory Okay, now if you attempt to execute the ransomware again, or before executing the ransomware, let's create a test file under this directory. So sudo nano a text file. Under the text file, we're going to say testing. Okay, now cat, and now we can see the file, or we can verify the file has been created successfully. Afterwards, or the next step, we're going to execute the ransomware. Sudo. So now, as you can see, we get the statement encrypting, and there were no errors returned. We're going to assume that the encryption process was executed successfully. To examine what happened, we're going to go to the directory itself, ls. As you can see, we have two files now. The first file, assuming that this file is the encrypted file. This is the encrypted form of the original file, test, right? As you can see, the extension is 24 bis file test. You can see this is the extension, and we can see there is another note. If we extract the contents of the note, we get this note: this file has been encrypted by base24 group. Please contact base24 proton mail to discuss payment for us, providing you the decryption software. Now, because you have analyzed the file and you were able to extract the decryption key, you will not need to contact these guys. You add the decryption key, proceed and create a script to decrypt the files. Now, one thing to note here is that it is the absence of the original file test. As you can see, we have two files only, a note file and another encrypted file. And that's because the original ransomware deletes the original files after encrypting them. Okay, so that's the analysis with AnyRun. You can stop this. As you can see in AnyRun, the file was labeled with malicious activity. If you go to VirusTotal and upload the file, you can see 32 AVs labeled the file as malicious out of 67. In the description, it says that, or most of the AVs state that the file is ransomware designed to run on Linux. Take a look at the community. Again, Yara, or the file, has actually triggered Yara signatures because it uses proton mail in the notes. That's one of the reasons. And at the details, we can see the hash, and we can see the header information and other details. Now, if you want to create detection rules for such ransomware, you're gonna have to rely on these information, such as the hash. All of these hashes can be used to create detection rules and maybe sigma rules, so that any attempt to open the file in the environment is recorded and maybe blocked. So guys, that was it.